This presentation is a part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. In this section, we are going to examine the constituents of classes, called members, as well as how access to members is controlled. So the basic building block of a class is what are called members. Each class consists of 0 or more members. There are three basic kinds of members. There's what's called a data member, a function member, and a type member. Data members basically define the representation of the class object. In other words, whatever internal state is associated with the class object is stored in using data members. Function members provide operations on class objects. And then type members specify any types that are associated with a class. So to use a random number generator class as an example, so suppose we have a class that generates random numbers, the data members for the class are going to be the internal state for the random number generator that's used to keep track of what is the next random number in the sequence that needs to be produced. The function members might be something like a member function to say, please give me the next random number in the random number sequence. In other words, it provides the operation of finding out what the next random number is in the sequence that's being generated. And then a type member might be used for something like specifying the particular type that's returned by the random number generator. Is it returning, for example, a result that's a double or an int or a long int or a long int or something like this? We can control the level of access that users of a class have to its members. And there are essentially three levels of access that can be provided: public, protected, and private access. So if a public member is a member that can be accessed by any code, so there's no restriction, it's open to everybody to access. At the other extreme, we have a private member of a class, which is a member that can be accessed only by other members of the class and friends of the class, which we'll be discussing shortly. We haven't discussed friends yet, but we'll be getting to that soon. There's also another level, what we call a protected member, and this relates to inheritance, another language feature that we'll be discussing much later. So for now, we're going to ignore protected access. And relating back to some terminology that I introduced earlier, the public members of a class constitute the class's interface. In other words, it's the part that's visible to the code outside of the class, the users of the class. On the other hand, the private members constitute the implementation of the class. It's details that are hidden from the outside world, in other words, the code outside of the class, and is only visible to the class itself and its friends, which we'll be talking about later. On this slide, we have another example illustrating the notion of friendship. So we have a class called widget, and it has a single data member called value, so the class basically stores an integer value for some purpose. And it has a single member function called setValue that allows you to essentially change the value of this value data member and also return its old value in the process. So the function returns an int, which is the old value before it set the value data member to this new value. Now, the class widget declares a function as a friend. So the function called wastetime that takes no parameters and returns void is a friend of the widget class. So the function wastetime has full access to all the members of this class, not just the public members, but the private members as well. So if we look at the code for wastetime function, the function that's a friend of the class, you'll notice that inside this function, we're doing some things that normally you wouldn't be able to do. You wouldn't be able to do unless wastetime was a friend of the class. In particular, we're creating a widget object called x inside this function, and then we're calling a private member function of the class, because if you look up above here, the member function doNothing is a private member, so it can only be called by the class widget itself or friends of the class. But because wastetime is declared as a friend of the class, it's allowed to access this private member function and invoke it. This next line, again, normally this is something that the code wouldn't be able to do because it's code outside of the class, so it can't access the private data member value, because if you look up above here, value is a private member. So normally this can only be accessed by code that's part of the widget class. But because wastetime, again, is a friend of the class, it's allowed to access this data member. So this line of code is valid. So both of these two lines of code here compile okay because of the fact that the wastetime function is a friend of the widget class. Now we have another function called func, which is not a friend of the widget class. And we have some code here. We create a widget variable called x, and then we try to invoke the setValueMember function of this widget. And this is okay because the setValueMember function is public, so it's accessible to all code. So this doesn't cause any problems. But this next line here is problematic. This will cause a compile error because in this case, this function func is trying to access a private data member of the widget class because value is a private member. If you look up above here, it appears after this private specifier. So value is private. So this function is not allowed to access this data member. This line of code will produce a compile error. Similarly, on this next line, the function func is not allowed to access or invoke the member function doNothing because doNothing is also a private member of the widget class. So only the widget class itself and friends of the widget class are allowed to invoke or access this function. Perhaps you might be wondering what happens if you don't specify any access specifier for members of a class. So for example, what happens if we define a class called myClass and then we don't actually specify any public or private access specifier here, and then we just start listing off members which are represented by this ... here. This is equivalent to writing the lines of code below. In other words, if we don't specify any access specifier here, it's the same as if we said private. In other words, members are private by default. Unless you explicitly indicate some other access specifier, they'll be private. So far, we have been introduced to the class keyword for specifying user-defined types. And for a class, member access is private by default. In C++, a user-defined type can also be specified using the struct keyword. And a struct is nothing more than a class where member access is public by default. So for example, in the code snippet that we have here, where we have struct widget, this introduces a user-defined type called widget. And in between the brace brackets for the struct is all of the members for that struct, just as we have with the case of a class. So the syntax for struct and class are identical essentially. And this particular code snippet at the top here with the struct keyword is identical to this second code snippet here using the class keyword. In other words, a struct is just a class where the members are public by default. So on this slide, we have a very simple example of a class. The class is called vector_2, and it represents a two-dimensional vector. In other words, a vector with an x component and a y component in two-dimensional space. We can see that there's two members that this class has, and they're data members. They're storing data. The first data member is called x, and it has type double, so it stores a value which has type double. And the second data member is called y, which is also of type double. And then we have some code down below here, a function called func, which is using a variable of the type vector2. It creates a variable of type vector2 called v. And then what I want to point out here is in order to access the data members of v, what we do is we use the member selection operator, which is the dot operator, this dot that appears here. So if I have a variable v and I want to access some of its data members, I put a dot and then the name of the data member I want to access. So v.x will give me access to the x part of the vector2 object. So we're saying v.x, we want to assign the value of 1 to it, so this will set the x part of the vector variable v to 1. And then here we want to access the y component, or the y part of the vector2 object, so we say v.y. Again, we're using the member selection operator to get access to a particular data member of this class object. So these are some examples of data members, x and y. On this slide, we have an example of a class called vector2. And this particular class, you can see that has two data members, x and y, similar to an earlier example that we had. In addition, though, we have the interesting thing on this slide is we have a function member now. This is a function, which is a member of the class, so it's called a function member. It's a function that takes two double parameters, which are denoted by x underscore and y underscore here, and it returns no value because the return type is void. And then we actually have the definition of the member function outside of the class. definition. So the class definition, it starts at this brace and ends at this brace. So this definition is outside of the class, which is normally the place where you'll tend to define the functions. And you can see that all this initialize function is doing, as the name sort of suggests, is it's just initializing the vector2 object. It's initializing, it's using x underscore, the value of x underscore, to initialize the x data member of the class, and it's using the parameter to the function y underscore to initialize the y data member of the class. And I have a simple little piece of code here, a function which is using a vector2 variable. So we have this vector2 object called v, and we initialize its value by calling the member function initialize. And the way we do this, if we want to access a member of a class object like v, we use the dot operator. So that we say v dot and then the name of the member function, which is called initialize, and then we provide the parameters to this member function, and it takes two double parameters, which is what we're passing here. You might notice some strange syntax here, this double colon. This double colon is called the scope resolution operator. The reason that we need this is because the definition of this function initialize, this definition here, is outside of the class body. There has to be a way for us to tell the compiler that this particular function is not just a function called initialize, it's the function initialize that actually belongs to the vector2 class. So what we do is we specify the name of the class here, followed by the scope resolution operator colon colon, followed by the name of the member function. And basically this is identifying not just any initialize function, but specifically the initialize function that belongs to vector2. And maybe one last thing to point out is a member function always has one implicit parameter that's not explicitly appearing in the list of parameters for the function. So this function initialize, although it looks like it only has two parameters, x and y, there's really a third parameter that doesn't appear explicitly. And the third parameter is actually the object on which you're performing the operation of initialization. And maybe to make this a little bit more concrete, if we look at this line of code here where we're invoking the initialize member function, notice that there's actually three things that are being given to initialize. There's the first parameter, explicit parameter to the function, the second explicit parameter to the function, but there's one other critical piece of information that's being given to the member function initialize, which is this object v. In other words, you can't call the initialize function unless you give it an object, in this case the object v, to operate on. And this particular parameter is sometimes referred to as an implicit parameter because it's always passed to member functions of a class. It always is passed. The object you're operating on is always passed to the member function, but it's not appearing explicitly in the parameter list here. But it's important to keep this in mind because it will lead to a better understanding of what's going on when you're using classes. As mentioned earlier, a member function always has a class object as an implicit parameter, namely the class object for which the member function is being invoked. This implicit parameter is accessible inside a member function through the this keyword. In particular, the this keyword is automatically defined inside a member function as a pointer to the implicit class object parameter. Inside a member function, data members can then be accessed through the this pointer. As a convenience, however, the language allows data members to be referred to directly by their names instead of using an expression involving the this keyword. For this reason, the use of the this keyword is not needed in many cases and normally omitted. Nevertheless, it's important to understand that in principle, the this pointer is being implicitly used to access data members even when not explicitly specified. So I have a code example to help illustrate some of these concepts a little bit further. So you have this class called widget. It has a single data member called value, which has type int, and has a single single function member called update value, which allows you to change the value of this data member value. So this function takes a single parameter, which is the new value for this data member value, and it returns the old value. So if we look at the code for this function, the very first thing that it does is it saves the old value of this data member by assigning the old value to this variable old value. And by the way, this name value here, notice that there is no local variable or any variable in this function that's visible that has the name value. So what the compiler does is it looks for a data member that has this name, and it notices that there is a data member that has this name. So what it assumes is that when you wrote value, in other words, this expression here, what you really meant is this arrow value. In other words, it's assuming it's a data member, therefore it has to go to where this pointer is pointing and access the object that is at that position in memory. Then we go on to the next line here. We update the data member value to the new value that we want it to have. Again, when the compiler sees this expression here, it notices that there is no identifier name or identifier that has the name value that's visible in this code here, in this function. Therefore, it looks for a data member with this name, and it notices that there is one, and it interprets this value as being this arrow value. In other words, it assumes it's a data member, and it goes to where this pointer is pointing and accesses the object that's there and extracts out the data member value. And then we return the old value that we had saved on this line up above here. Then I have some code down below that's using this particular class. So it creates a widget object called X. And then for this data member, or for this object X, it calls update value, passing the parameter of 5. So this is going to say we want to set the new value of our value data member to 5, because that's the parameter that we're passing in here. And when this function actually executes, the value of this, the pointer this, is going to be the address of X, because the implicit parameter that is passed into the update value function, when we invoke it in this way, the implicit parameter will refer to the object that we're operating on, which in this case is the object X. So inside the function widget update value, when we call it, the variable this, or the keyword this, is going to refer to the address of X. Earlier we talked about the const qualifier, which is essentially used to indicate the notion of constantness, the notion that something can't be changed, or the code is making a promise not to change some quantity. Now, member functions always have an implicit parameter, which is the object that's being operated on by the member function. And before I go through the rest of the bullets on this slide, I want to go down and look at the code example below. Then I'll come back to the bullets at the top of the slide and make some additional comments. So in this code example, we have a class called counter, which is basically just implementing a simple counter. The only data member is just a single data member called count. It has type int, which is representing the counter value for the counter. And we have a very simple interface. We have 3 public member functions: getCount, setCount, and incrementCount. getCount just returns the current value of the counter. setCount sets the current value of the counter to some new value, which is passed in as a parameter to the function. And incrementCount just increments the value of the counter. So this is basically what the counter class does. Now, if I go back to and look at the getCount member function in a little bit more detail, notice that there's no explicit parameters in the parameter list to getCount. Nevertheless, there is an implicit parameter that's always passed into this function, which is the actual object on which you're operating. When you call getCount, you have to give it an object, a counter object, for which you're going to extract its count value and return it. You can't call getCount by itself without giving any parameters, implicit or explicit, to it, because it wouldn't know what object it's operating on. So there's an implicit parameter, which is again associated with this pointer. And in fact, we could write this code, the actual body of this member function, instead of writing it as return count, we could replace count by this pointing at count. And in fact, this is really what the code that we've written means. It's just a short form for this longer version here. So when we say return count, we're really saying return this arrow count, meaning go to where follow this pointer, go to where it's pointing, and it's going to be pointing to an object of type counter, and then we access the value that's there and extract out the data member count. Now, we need to be able to distinguish the case that this pointer is either a pointer to something that's const versus the case where it's a pointer to something that's not const. In other words, we have to distinguish between the case where we're allowed to change the thing that this pointer points to, or we're not allowed to change the thing that this pointer points to. And the way that we do this is we can, or in the case that we want to indicate that the thing that this pointer points to is const, we're not allowed to change it, we need to add the keyword const somewhere. But the question is, well, where do we add it? Because there is no explicit parameter appearing in the parameter list for getCount here where we can stick on a const. Well, the answer to the question, where do we put it, you can sort of maybe guess from what appears here in the code. We have this const appearing here after the parameter list. What this const is referring to, it's referring to the thing that this pointer points to. In other words, it's referring to the object that's actually being operated on by getCount. So by putting this const keyword here, what we're saying is getCount is not allowed to change the object it's operating on. In other words, when we invoke getCount, we have to give it a counter object to operate on, and it's not allowed to change that object. And this makes sense because the whole point of getCount is just to look at what the current count value is. It should never change the value of the counter just by looking at it. So it makes sense that this member function should be const, and this is what we call a const member function. A const member function is simply a member function that is not allowed to change the value of the object it's operating on. If we look at the next member function here, setCount, the whole purpose for this function to exist is so that you can change the value of the counter. Because of this, it wouldn't make sense to make this a const member function. Notice that there's no const appearing here, meaning that this member function is not a const member function, meaning that this member function is allowed to change the object it's operating on. It's allowed to change the counter. And this makes sense because this is exactly what the function is trying to do, right? It's one line of code, and all it's trying to do is change the value of the count, the value of the counter. And if we move on to the increment count function, this function here also, you'll notice it's not a const member function. There's no const keyword here. But this makes sense because the whole reason for this function to exist is so that you can increment the count value. In other words, you're trying to change the counter value. Therefore, it wouldn't make sense to make this member function const, because if you made it const, you'd be saying this function is not allowed to change the value of the counter, but clearly incrementing the counter is changing its value. So this is what's meant by const member function versus non-const member function. I just want to show a little bit more go through a little bit more of this code example just to illustrate some other issues with respect to constness to be careful of. It's very important when you define member functions or declare member functions that you choose the constness appropriately. In the case where the member function should be const, you make it const. In cases where it shouldn't be const, don't make it const. If you mix these things up, you can run into all the same sorts of problems that have been discussed earlier when you mix up the constness of things. In other words, if your code is not const correct, as it's sometimes called. So we have this function func here. It creates a counter variable called CTR, so basically an object of this class up above here called CTR. Then we invoke for this CTR object, we invoke setCount to set the count value to 0, and this is fine. Then we proceed on to read out the value of the count from this counter variable by calling the getCount member function, and we're operating on the CTR object in this case. So it's going to return the count for the CTR object, and we assign it to this int variable. And then the main part of this example really that's important is the last two lines here. So here we're going to create a reference, a constant reference to CTR called CTR2 or counter2. And the important thing here is it's a const reference. So what this means is that CTR2 is not allowed to be changed under any circumstances. By writing this line of code, const counter ref CTR2 equals CTR, we're making the promise that we will not under any circumstances change the value of CTR2. What this implies, and it's important to understand this, what this implies is the compiler will not let us invoke any non-const member function for CTR2, because a non-const member function is a member function that does not promise to not change the object. Because it's not making it wouldn't be making the promise not to change the object, it would be dangerous for the compiler to let us invoke such a member function, because the member function might try to change the thing that's const, and the compiler takes constness very seriously and does not want to allow us to change something that's const. So if we go on to the next line here, this next line compiles fine and there's no problem with it. But the subtlety here I want to point out, it's really, really important that this getCount member function be const. In other words, it's really important that this const qualifier appear here. If we took this out, this line of code here would fail to compile, and it's really important to understand why it would fail to compile. The reason why it would fail to compile is because we've said, by the way that we've declared the variable CTR2, this reference, we've said that it's const. So this means CTR2 under no circumstances is allowed to be changed. If, however, the getCount member function was a non-const member function, in other words, we took out this const here, by taking out the const here, what this is saying is this function is allowed to change the object. So get count can actually change the value of this count data member if we take out this const qualifier here. So if this was taken out, what that means is that this function can now change CTR2, but the compiler, when it sees this, it would say, hey, I know what you're doing. You're just trying to find a sleazy backdoor, indirect way to change this thing that's const. So it will fail to compile this line and say error, this is an error. You're trying to change something that's const. So again, this is why it becomes very important when you're writing member functions to make sure you get the constness of the member functions correctly. Because, for example, if we left out the const qualifier here, this line of code would fail to compile, even though it's a perfectly reasonable line of code, nothing wrong with it. But it would fail to compile because the compiler would be thinking that this function might change CTR2, therefore, because CTR2 is const, I can't let you invoke this function. So again, it's very important to make sure that you get the constness of member functions correct. If the member function should be const, you make it const. If it shouldn't be const, then don't make it const. Earlier when we were discussing functions, we talked about inline functions. Because member functions in a class are also a type of function, they can also be inlined. And when you define functions inside the class body, so by class body I mean the things between the brace brackets when you introduce a class. So we say class, my integer, everything between the brace brackets is what I'm referring to as the class body. If you define as opposed to declare, but if you define functions, member functions inside the class body, they're automatically inline. So in other words, if I write code like this, it's as if I'm putting the keyword inline in front of this function. This function will be inlined. In other words, this code here is exactly equivalent to this code here. The only thing I've done is I've taken the definition of this set value member function and defined it outside the class body, and I put inline in front of it. So these two pieces of code are exactly identical in terms of their meaning. This is a very important thing to keep in mind because I find that one common mistake that people who are new to C++ often make is they always put the definitions of member functions inside the class body, and this is a bad thing because basically what it's doing is it's telling the compiler, please inline my entire program, like inline everything in all of my classes. And usually you don't want to inline everything because quite typically classes will have some larger functions which wouldn't make sense to inline. The good news is a smart compiler will probably ignore you and say, you're being ridiculous trying to inline your entire program and I'm going to ignore you. But it's always better not to rely on compilers to save you from your own stupidity. It's better to just to not do stupid things in the first place. So for this reason, unless you really want a function to be inline, don't ever define it inside the class body. Otherwise, it's inlined and there's nothing you can do about it. Again, a class can have a number of kinds of members. We talked about data members and function members. There's also what are called type members. On this slide, I have an example of a class called point2, so it represents a point in two-dimensional space. It has a data member which represents the x-coordinate and a data member that represents the y-coordinate of the point. But I also have a type member as well. Coordinate is an example of a type member. So I've created a name for a type called coordinate. It's just an alias for the type double. And then I'm saying that this data member x has type coordinate and the data member y has type coordinate. So it's basically equivalent to saying double x, double y. But the benefit this has is that later on, for example, if you decided that you wanted to change the coordinate type to be float or long double, you only have to change one line of code instead of more lines of code. Here you just would change double to say float or change double to long double, and then you don't have to change all of the other lines in code. If this was a much bigger class with many other lines of code where you had double all over the place, you'd have to change double everywhere else. So it provides a very convenient way to make it easier to change the class. Also, it makes the class more readable because when you see coordinate here, it's obvious that x is a coordinate. You don't, if you just had double x instead, well, double could mean lots of different things. So it's maybe not as clear what x might be. But if you say coordinate here, using essentially a symbolic name for the type, it makes the intent behind the code more clear. And then we have an example of a function here which is using object of type point2, so it creates this variable p of type point2. And just to use an example here, we're trying to create a local variable inside this function which has the coordinate type for its type. So we're trying to create this local variable x, and we want the type of x to match the type of the coordinate type that's used by the point2 class. Notice here that we have to use the scope resolution operator. We can't just write coordinate by itself. because if we write coordinate by itself, there's no way for the compiler to know that we're talking specifically about the type called coordinate that's inside the point2 class. So in order to specify that we're talking about the coordinate type that's specifically in the point2 class, we have to say point2 : coordinate. So this is saying the coordinate type that's inside the class point_2. As discussed earlier, the private members of a class can only be accessed normally by the class itself. But sometimes we might want to grant access to private members to another class or a function which is outside the class. And for this purpose, the C++ language provides something known as friends. So a friend of a class is either a function outside the class or another class entirely that's allowed to access the private members of a class. And to make a function or a class a friend of another class, we use a friend statement. So I have a small example on this slide here. We have two classes, one called gadget and one called widget. And the basic idea here is widget has some private members. I'm not showing them here, but they're basically represented by the ... here. So there's some private members in the widget class. And we want the gadget class, for example, to be able to have full access to all the members of the widget class, including all of the widget class's private members. So normally this isn't allowed. Normally the gadget class would not be able to access the private members of the widget class. But what we can do is we can add a friend statement to the widget class, in particular this line of code here, which says that the gadget class is a friend of the widget class. And by adding this line here, we're essentially granting access to the gadget class so that the gadget class can access all of the members of the widget class, including the private members. We can also do a similar thing with functions as well. So if we have a function, for example, the function myfunc is a function outside of the widget class, some other piece of code, and we want to give it full access to all of the members of the widget class. So we can make this function myfunc a friend of the widget class, and we do this again using a friend statement. So we have friend followed by the declaration of the function that's going to be a friend. So it's a function that takes no parameters and returns void, and it's called myfunc. So this function here, wherever the code happens to be in your program, has full access to all of the members of the widget class, including the private members. On this slide, we have another example illustrating the notion of friendship. So we have a class called widget, and it has a single data member called value. So the class basically stores an integer value for some purpose. And it has a single member function called setValue that allows you to essentially change the value of this value data member and also return its old value in the process. So the function returns an int, which is the old value before it set the value data member to this new value. Now the class widget declares a function as a friend. So the function called wastetime that takes no parameters and returns void is a friend of the widget class. So the function wastetime has full access to all the members of this class, not just the public members, but the private members as well. So if we look at the code for wastetime function, the function that's a friend of the class, you'll notice that inside this function we're doing some things that normally you wouldn't be able to do. You wouldn't be able to do unless wastetime was a friend of the class. In particular, we're creating a widget object called x inside this function, and then we're calling a private member function of the class, because if you look up above here, the member function doNothing is a private member, so it can only be called by the class widget itself or friends of the class. But because wastetime is declared as a friend of the class, it's allowed to access this private member function and invoke it. This next line, again, normally this is something that the code wouldn't be able to do because it's code outside of the class, so it can't access the private data member value, because if you look up above here, value is a private member. So normally this can only be accessed by code that's part of the widget class. But because wastetime, again, is a friend of the class, it's allowed to access this data member. So this line of code is valid. So both of these two lines of code here compile okay because of the fact that the wastetime function is a friend of the widget class. Now we have another function called func, which is not a friend of the widget class. And we have some code here. We create a widget variable called x, and then we try to invoke the setValue member function of this widget. And this is okay because the setValue member function is public, so it's accessible to all code. So this doesn't cause any problems. But this next line here is problematic. This will cause a compile error because in this case, this function func is trying to access a private data member of the widget class because value is a private member. If you look up above here, it appears after this private specifier. So value is private. So this function is not allowed to access this data member. This line of code will produce a compile error. Similarly, on this next line, the function func is not allowed to access or invoke the member function doNothing because doNothing is also a private member of the widget class. So only the widget class itself and friends of the widget class are allowed to invoke or access this function.